Hello, can you just let me know if you can see the presentation?
Yes, sir.
Yes, sir.
Yes, sir. Okay. So let's put it in full screen mode so that you are able to understand a little better. Okay. So we are going to have a look at some of the sensors that are commonly used in IoT. So as you can see, we talked about something on radar and lidar systems in the previous class, right? So we will continue to see some other type of sensors as well. And since I am in full screen mode, please let me know if I drop out or if you have any um, if I have any if there are any network issues or anything of that sort. Okay, so please let me know immediately, and we'll start now. So the idea is we have multiple types of sensors. We have seen two different sensors in automotive industry, which will be very relevant in, which are already very relevant, but they will become more relevant once once the V2V communication and V2X communication systems, which are enabled through IoT, become more popular in the, and this is likely to happen in the near future as the 5G rollout happens. Okay, why do I insist so much on 5G? Any ideas? Data speed is one thing, but other than that, why do we say why are so many all the companies so excited about 5G? Do you have any suggestions on that? Any ideas? Hello? Anyone? Am I audible?
Yes, sir.
Yeah. So, any suggestions on why the industry is so kind of interested about 5G? What specific upgrades does it offer when compared to say 4G? Any suggestions?
Direct communication between edge nodes.
Yes, that is the critical part of why the industry is so interested about 5G, because it will provide you to do device to device communication. D2D communication will be possible once the 5G protocol stack is implemented. What that means is that you will not need to go through the cellular network tower and through the whole backend and then come back and transmit data to somebody who's sitting just next to you. So device to device communication will become feasible if you have 5G network. And that basically means that you should be able to create ad hoc networks, such as the one that gets formed when you have multiple cars in the same locality. They can share information. Cars ahead can tell what is the congestion to the cars which are kind of driving behind. So alternate routes can be arranged for, collisions can be detected and warned. So all those things are possible when you have 5G systems, device to device communication. That is the key factor which is going to drive 5G. Okay, so that is good. And we, we have already seen these two videos in the previous class. We will go to the next one, which is on potentiometers and proximity sensors. Some of you already know what are potentiometers, what are proximity sensors. uh, a lot of you already have a good idea of that, right? But there are several types of potentiometers and several types of proximity sensors. Not all of you may be knowing all of it, so I thought it will be a good idea if I give you some understanding of what this is about. Okay, so let's have a look at potentiometers first. What is it, how do they work, and what are the applications that they're used for?
A potentiometer, or even simpler pot, is a manually adjustable variable resistor with 3 terminals.
Is the audio okay?
To be more specific, we can say that 2 terminals are connected to the ends of a resistive element, and the
Yes.
third one is connected to a wiper that slides over the resistive element. Therefore, the wiper position defines the output voltage. These are the symbols used in circuit drawings. Left is the American standard, and right the international one. Here you see another example of a potentiometer, and I will explain more in detail how they function with this schematic drawing. There is a resistive element that can have different constructions, such as carbon composition or wire wound. Then there is a wiper that rotates and slides over the resistive element. There are 3 terminals. One is connected to the wiper and the other 2 to the ends of the resistor. The complete mechanism is protected by a housing. The potentiometer can be used as a voltage divider to obtain a manually adjustable output voltage at the slider from a fixed input voltage applied across the 2 ends of the potentiometer. This is the most common use of them. The circuit has a voltage source, Vs, and a load with a resistance, RL. In this case, the load is a lamp. We have connected the first terminal to the positive leg, the second to the wiper, and the third one to the negative lead. Now we created in a pot meter 2 resistive pads. Basically, we could say that each represents a separate resistor. To make our representation simpler, we replace it with resistor R1 and R2. If we change the position of the wiper, we change the values of resistor 1 and 2. We can also see that the current through our lamp changes, causing it to light up. With basic network theory for resistors in series and parallel, we can calculate the voltage across the load. Suppose that the load resistance is much higher than the potentiometer resistance. The formula can be simplified into VL is R2 divided over R1 plus R2 times Vs. If the wiper is on one end and R1 is 0, it means that the voltage through the load is the same as the source voltage. If the wiper is on the other end, R2 is 0, which causes the load voltage to be 0. This ability to adjust from 0 to 100% is an advantage of the potentiometer over a variable resistor in series with the load. The second advantage of the potentiometer over the rheostat is that the ratio of resistance of the potentiometer and the load is less critical. For the rheostat, a big or small load could make the rheostat resistance excessive or negligible. When selecting a potentiometer, there are some important characteristics to take note of. The taper is the ratio between the wiper position and the resistance ratio.
I will pause this right here. What he is going to tell now is very important as far as selection of the potentiometer is concerned. Okay, so please pay very good attention to this. This may not have been taught to you in the class, but this makes a lot of sense from practical viewpoint. Okay, is this okay? So far, was it audible to you?
Yes, sir.
Yes. So pay attention to the next segment. Okay, very important.
The most common are the linear taper and the logarithmic or audio taper. A marking code on the device indicates its resistance value. If you see, for example, 100K, it means the resistance is 100 kiloohms. Also, other marking systems are used, such as the SMD marking with 3 digits. In this case, the first 2 digits indicate the resistance value, and the third the multiplication factor. So 10 ohms times 10 to the power of 2 is 1 kiloohm. The taper is marked with a number, which is different according to the part of the world. A good practice is to check the value in the taper by measurement. If we turn the wiper, the value changes. The smallest possible change we can measure is called the resolution. An example of a good resolution are conductive plastic potentiometers, while wire wound has often less resolution. Also, the wiper design influences the resolution. On the ends of the resistor, low resistance metal parts are connected. When the wiper enters these parts, there will be a jump in resistance. This is called the hop-on or hop-off resistance. Potentiometers are constructed in many different ways. I will shortly go through the main variations. The most common type are the rotary ones. The single turn pot is the most common rotary pot and can usually rotate 3/4 of a full turn. The multi-turn can make multiple rotations. 5, 10 and 20 are the most common. Because of the longer travel, the precision is higher. A dual gang has 2 resistive elements connected to one shaft. In this way, 2 channels can be set at the same time. A concentric pot is also a dual pot but has 2 concentric shafts. Both pots can therefore be adjusted separately. A servo pot is motorized and can be actuated by a motor, and usually also by hand. The second category is the linear pot meter. The slide pot has a single linear wiper and is also known as fader. A dual slide pod has one slider that actuates 2 pod meters in parallel. A multi-turn slide is adjusted by rotation. A spindle transforms the rotation in a linear motion of the wiper. And finally, a motorized fader is actuated by a servo. The third category is the digital potentiometer. These are controlled electronically and exist out of an array of small resistive elements in series. Each of these elements has a switch. Therefore, you could say that these switches function as a virtual wiper. The fourth category is the rheostat. Basically, it is a single variable resistor. If we take a potentiometer and we connect only the wiper and one of the other terminals, we created a rheostat. For the resistive element, different materials can be used. Carbon composition is most common, has a low cost, and a reasonable noise and wear. On the downside, they are not very accurate. The wire wound can handle high power, is durable and long-lasting, and can be very precise. They are often used in high-power applications. The drawbacks are the limited resolution and the rough feel. Conductive plastic has a very smooth action, the highest resolution and a long life. Unfortunately, they handle only low power and can be expensive. They are often used in high-end audio applications. Cermet is very stable, has a low temperature coefficient and can handle high temperatures. On the downside, they are expensive and wear out faster than other types. They are often used for trim pots, which do not have to be adjusted often. Potentiometers are used in a wide variety of applications. For example, in automotive, the throttle pedal is often a potentiometer. Another example is joysticks for machine control. Volume control is often performed with a motorized potentiometer in audio applications. For balance control, a dual gang potentiometer can be used, where one gang has a logarithmic taper and the other gang has an inverse logarithmic taper. Potentiometers are often used as position or angle transducer to measure distances or angles. In fabrication and calibration, trim pots are often used. Trim pots are preset potentiometers, which are often mounted on a circuit board and can be used to tune or adjust the circuit's performance. They are used only during calibration of the system and are at a fixed position most of the time. If you want to learn more about potentiometers or other resistor types, please visit resistorguide.com.
Okay, any queries that you would like to ask now on this? Was this of any use? You are able to now see the variety of the potentiometers that are used.
Yes, sir.
Yeah, and you have to choose your potentiometer based on your applications, right? As I said, when you are having a throttle position sensor for your automotive vehicle, you will use the ones which are provided by OEMs like, not OEMs, by manufacturers like Bosch. And when you have like high power applications, you use wire wound. When you don't require that, you use ceramic. Sorry, not ceramic, the plastic type, and all those kind of applications do exist. So choosing a potentiometer is a very important part of your device selection. Do not try to use you cannot use pots interchangeably based on like just randomly like that. Trimmers are typically preferred when you are trying to tune the resistance and keeping the resistance constant after that. So if you just replace it with the normal pot that you can rotate all the time, that is not going to be good. So you have to choose accordingly. That is one takeaway from the the video that we have seen. Okay, so can we move on to the next one? Hello?
Yes, sir.
Yes, so we go to the next video. This is about what is proximity sensing and how it is done. Proximity sensors are very widely used in the industry, mainly to make sure that to detect the absence or presence of material in the neighborhood. So most of the pick and place robots that you will find in the industry are triggered with the help of this kind of devices. or if you want to find out if an item is available on the conveyor belt or not, they use proximity sensors. All these, there are hundreds of applications of proximity sensors that are available in the industry. And you can also buy proximity sensors without a great deal of trouble from the internet. Most of them will be operating on 24 volts. Some 12 volt devices are also available, but you will not find a lot of them working on 5 volts or smaller ones. Okay, because most of the industrial supplies work on 24 volts or at worst 12 volts. So you will find most of these proximity sensors being working on 24 volt DC. So let's get started with that very quickly. Just have got it.
A proximity sensor is a sensor able to detect the presence of nearby objects without any physical contact. A proximity sensor often emits an electromagnetic field or a beam of electromagnetic radiation, infrared for instance, and looks for changes in the field or return signal. The object being sensed is often referred to as the proximity sensor's target. Depending on the proximity sensor targets, different sensors may be used. For example, an inductive proximity sensor requires a metal target, whereas a capacitive photoelectric sensor may be suitable for a plastic target. Proximity sensors have a long functional life and high reliability due to the absence of mechanical parts and the lack of physical contact between the sensor and the target. A proximity sensor that is adjusted to a very short range can often be used as a touch switch. Proximity sensors are commonly used in industrial applications, from manufacturing and food production to recycling. They are also used in vehicles for detecting the proximity of other vehicles relative to one's own car, as well as for parking assist functions. In mobile devices, especially phones, the proximity sensor is used to detect whether a user's face is close to the phone during a phone call, prompting the screen to turn off to prevent false touches on the touchscreen. Stay tuned to Galco TV for more tech tips, and be sure to visit galco.com to view our full product catalog.
All right, so was the video audible to all of you?
Yes, sir.
Yes. So this is the idea of a proximity sensor, and you can see it is very, very popular and very widely used. So even when you are developing an IoT based system, the primary sensing element in most of the cases will be a proximity sensor. One extreme example of proximity sensor that they list out is the ultrasonic sensor that you have in your car. The car reversing sensor that you have is typically an ultrasonic sensor. Okay, so its resolution is poor, but still you have that. But most of the typical industry applications of proximity sensors do not require them to detect the range of the obstacle, but they are used only to detect the absence or presence of the obstacle, or kind of an item which they are trying to detect. So as you can see, the robotic arm that was there, the robotic arm was initiated when the item was present, and the item presence of that item was detected with the help of a proximity sensor, or typically you call it as a proximity switch. Okay, because it's either on or off. So if it's on, something is there. If it is off, there is no obstacle or no object there in the vicinity, and so you can initiate or stop the robot from picking or placing it. So that is the idea of a proximity sensor. Okay, so can we go to the next one? Any queries?
No, sir.
No. Okay, so let's go to the next slide. This is going to be slightly more interesting, because what we are going to see in the next slide.
A potentiometer, or even
Okay, so what we are going to see in this slide is more important, because flow measurement is something which is extremely widely used in the industry. Typically, whenever you talk about industrial measurements, or whenever you are trying to measure something, you either end up measuring flow, temperature, or pressure. These three are the most common measurement, what is it, the measurements that are made in the industry as well as in the environment. Okay, so first what I will do is I will give you an idea of one implementation of flow sensor in real world, and then we will go on to the learning the basics of flow meters. We do not have sufficient amount of time to do this, but I'll just give you a short overview of what flow meters are and for what type of flows, what type of flow meters are useful. You cannot use all types of flow meters for all kinds of applications. That is very, very important. If you are interested in knowing more about different types of flow meters, I will suggest that you refer to something, a very important book, which is called the Instrument Engineer's Handbook by B.G. Liptak, Liptak. It's available as a reference book in the library. You may also be able to kind of get it downloaded from the internet, but it's a very, very important handbook as far as instrumentation engineers are concerned, and there is a whole section on flow meters, their advantages, their disadvantages, what can be used and what cannot be used. So it's a very important aspect of instrumentation engineering, or for anyone who's willing to work with measurement of any kind of flow. All right, so let's get started with a basic flow meter application. So what this guy is trying to do is he's trying to measure the flow rate of water inside a small stream. Okay, so it's a flowing stream, he wants to measure the flow. So this is how the whole process is. Let's get started. Let's see.
This is the IoT flow meter. You just saw a video of it deployed to the river where it was gathering measurements, but here's the entire system outside of water so you can see how it's built. What we have here is a PVC pipe structure that holds both the electronics and the sensors for the system. Down here, we have a liquid flow meter that has a 3D printed funnel and a 3D printed bracket attached to it. That bracket holds it submerged under the river water so that the water gets fed into the funnel and spins the pinwheel inside the sensor. Above the water, held on this PVC vertical pipe, is the housing for the electronics, which includes the Raspberry Pi, the 3G modem, and the external battery. This is held outside the water, so it's protected from any water damage and allows the 3G modem to connect to the cell service so it could push measurements to the cloud. So here's another look at the components that make up the system when they're not connected to the PVC pipe structure. Here we've got the flow meter. This is held submerged underwater. The water flows through one end and spins the pinwheel that's encased inside its housing. The flow meter itself is connected to the Raspberry Pi. On the Pi is a Python script that calculates how fast that pinwheel is spinning and allows us to calculate how many liters per minute are flowing through the sensor. The Pi itself is powered by an external battery, and also connected to the Pi is a 3G USB modem with a Soracom global SIM card in it, and that's what provides the internet connectivity that allows us to push measurements to the cloud. When the data from the IoT flow meter is sent to the cloud, it becomes viewable within Soracom Harvest, which we're looking at right now. Harvest provides a way to graph and plot the incoming data, which allows us to view it in real time and look at trends as new data streams in. For example, right here, we're looking at an 8-hour window for when the IoT flow meter was in a river and streaming out data on 1-minute intervals. So this gets plotted and we're able to monitor it as it's happening and then go back and look at it later to do trend analysis. And the data is captured and provided here for us to easily view it.
All right. So, does this give you an idea of how you can use flow meters with IoT for measurement of parameters? Hello.
Yes, sir.
Yes. So this is one simple application. Again, these people are also using Raspberry Pi. So this is a very simple example of how IoT can be used for measurement of flow. Even though this is an open channel kind of flow measurement, this is possible to do. Okay. So when you talk about flow meters, there are multiple kinds of flow meters. What you saw in the video that was just played was the typical type of flow meter that you can buy from the market over maybe Amazon or Flipkart. Okay, so what this kind of flow meters expect is that the water which is going to go into the flow meter is going to be clear. It's going to be free of mud. There will be no dust, there will be no dirt. So many requirements are there for it to work. And please remember the meter that they're talking about is something about the pinwheel type is what he was saying. What it is, it's paddle type, or it can be called as a turbine type flow meter, which has a magnet, and as there's a fan inside the flow meter. So when the fan inside the flow meter rotates because of the water flowing through it, the fan will actually cut the magnetic field of the magnet that is sitting there, and then you will be measuring that as pulses. So it's like a proximity sensor, right? So every time a fan blade cuts it, you measure the pulse. So the number of pulses that you get per time indicates what is the flow rate, and that is transmitted either as a digital output or an I2C signal or whatever signal you may have generated as a part of the reprocessing. And that's how the measurements happen. But what if your flow fluid is different from a pure water, or you want to do something practically, right? So the device that they had actually put was also not a very practical instrument, because they are measuring it in a river. There's a good chance that any time a small pebble could come and block the flow meter, or there could be dirt. After some time the dirt could actually clog the flow meter. So all those things could have happened, and I'm kind of 90% sure that over a period of time that would have happened. So those kind of flow meters are not very useful in a practical sense. For your mini project, or to just show that you are doing some IoT project, that is good, but you will have several issues eventually, right? So we'll have a look at what are the different types of flow meters which you can implement, because flow meter is a primary sensing element, right? After that, the IoT network you can implement with the same structure that they showed in that video also. But if your primary sensing element, which is your flow meter, is not correct, or if it is failing, the whole network becomes pointless. Correct? So that is the issue. So shall we get started with the flow meters? If you have any queries, please ask now. Anything?
No, sir, you can see next.
Okay, I'll proceed now. Okay. So just have a look at the flow meters. Okay, so did you have a look at this, and was this any use?
Yes, sir.
If you have any queries,
Yes,
please let me know. Please remember, we are trying to measure flow either through pipes or through some kind of a channel. Okay, there are two ways in which there are two ways of fluid actually trying to flow. One is through closed pipes, and second is through open channels. The flow of river or flow of streams or through canals is called flow through open channels. Okay, so open channel flow measurement is different from the traditional flow measurement, which is done through closed pipes. So almost all the flow measurement applications you will find will be for measuring flow through closed pipes. Okay, that is why you will find all the flow meters of that type. Flow through open channels have a different way of measurement. It requires some construction also, civil construction also is required. But yes, you can do measurements through open channels also. But for most practical applications where IoT deployments are needed, it will be through flow in closed channels. So these kind of flow meters are very relevant. Okay, any questions?
Sir, actually, I have a question, sir.
Okay, go ahead.
So, will the flow meter reduce the flow rate? For example,
Yes.
in positive displacement flow meter, will it reduce the flow of the water? Reduce the speed of the reduce the speed of the water while measuring its flow?
Yes, yes, this will happen. Uh, I don't know who asked the question.
Karthikeyan, sir.
Karthikeyan, okay. Yes, that is a major problem that we have, right? Because the most commonly used flow meters that you will find in the industry or in practice are called as differential pressure flow meters. So what does this do is that it creates an obstacle in the path of the flow, and whenever there is an obstacle in the path of the flow of water through a pipe, water or any fluid through the pipe, there is a pressure drop. So this is like the Bernoulli's theorem, right? So what happens is that when you constrict the flow of fluid through a pipe, its velocity will increase. You know that principle, right? So that's
Yes,
what you do
yes,
with your garden hose, no?
yes, sir.
Yeah, so this pressure difference that is created is directly proportional to the flow rate of the fluid. And for this measurement, you are actually creating an obstacle in the path of the flow. So flow rate will definitely be decreased. So you are perfectly correct. There will be a decrease in the flow whenever a flow meter is in the path. So if you want to minimize the flow measurement or the flow rate drop, or basically it's called the pressure drop. So if you want to minimize the amount of pressure drop through the pipe, you may have to use specific types of flow meters. There is something called a pitot tube, P-I-T-O-T, pitot tube, which kind of provides a very small obstruction in the path of the flow. So these type of flow meters, pitot tube type flow meters or ultrasonic type flow meters, which do not actually interfere with the flow measurement directly, those kind of flow meters are relevant. But the differential pressure type flow meters like the Venturi meter, the orifice meter, etc., they all actually kind of cause a lot of pressure drop.
Okay,
So
sir.
on the upstream side, the problem is that you will need a lot more pumping power because you are losing power in between, losing the flow rate in between. So yes, it's a major challenge. You have spotted a correct problem.
Okay, sir. Got it. Thank you, sir.
So any other questions?
No, sir.
Yes, the thing is that I may whenever I am explaining, I may explain as if like a few things that may be obvious because I have worked with these kind of instrumentation systems for a very long period of time. So there are a lot of things which may appear to be trivial to me, but you may be learning it or hearing of it for the first time. Okay, so please stop me in between if you are not able to understand anything, because like I mean, like if you are used to something for a very long period of time, it seems very trivial to you, but for someone who's learning new, it may not be that easy, right? So if there are things which you do not understand or you are not able to follow, please stop me and you can okay. So please let me know if you do, if you kind of have any issues. You can interrupt me in between. I don't have any issues with that. Okay. So shall we move on to the next type of measurement? And
Yes, sir.
hello. Yes. Okay. So let's get started with the next type of measurement. We are going to look at accelerometers. This is very popular, right? Almost all of you have worked with different kinds of accelerometers. Have you done any kind of experiments with accelerometers before?
Yes, sir.
Yeah, ADXL kind of accelerometers and other things. Some built into Arduino, some not built into Arduino, those kind of things. I think, can I see a show of hands? How many of you have done at least one experiment with an accelerometer? As a hobby or as a part of the syllabus? Any kind of accelerometer.
Hobby, sir.
Huh? You sure you're saying something?
Sir, I tried.
No, I did not get that. I got only half of the sentence. Kishore, please go ahead and complete the sentence. I could not hear you.
Sir, someone muted me in between, sir. That's it.
Yeah, please don't do that. Okay. So how many of you, can I see just a show of hands, please? How many of you have had some idea about the accelerometer? Okay, that is a very low number. Okay, so what we will go do is we will try to see what are the types of accelerometers available and what are they used for in both industry as well as in hobby kind of a scenario. Okay, so let's see that slide and questions once we are done with it. So I'll first start with what you can do with accelerometers in the industry. Accelerometers are very, very popular in the industry, and we will see how they can be used. Okay.
An accelerometer is an electromechanical device that can convert mechanical forces such as motion, vibration, and shock into an electrical signal that can be measured and recorded. In the industrial sector, where vibration levels must be monitored to ensure that machinery is operating at peak efficiency, piezoelectric accelerometers are the most widely used vibration sensors out there. There are many different form factors among piezoelectric accelerometers, but the one thing they all have in common is the piezoelectric element. Here's how it works. In this industrial vibration sensor, the piezoelectric element is attached to a weight called the sensor mass, forming what's called a spring mass system in the sensor. When vibration is applied to the system through the base, the mass produces an alternating force on the piezo element, which produces an electrical charge proportional to the vibration velocity and frequency. An integrated amplifier converts the charge into a usable voltage signal that can be read by a vibration meter. Because of their wide frequency response, good sensitivity, and easy installation, piezoelectric accelerometers can be found in many industrial and scientific applications, such as measuring low-frequency vibrations in robotics, in automotive applications detecting engine vibrations, in industrial and HVAC systems monitoring electric motor vibrations, detecting high-frequency vibration in gear noise analysis and turbine monitoring, high-impact shock testing, as well as measuring seismic vibration levels on roads and bridges to tidal forces and even earthquakes. Looking for accelerometers for your application? Call or chat online at omega.com. Thanks for watching and be sure to like and subscribe.
Okay. Any questions on that? Industrial accelerometers?
No, sir.
Okay. So what we are seeing is the practical application of accelerometers in the industry. Right, accelerometers are very popular in the industry. Mainly, the applications were listed out in the video itself. So some of the things that we use are for condition monitoring. So this is called machine condition monitoring because the typically the condition of machines can be identified with the help of the vibration levels that they produce. Vibration signatures of machines are different for different kinds of faults or problems that are arising in a machine. So accelerometers are one very good way of measuring those vibrations. And then what we usually use is we put some kind of machine learning algorithms in the back end, which will actually process these vibration signals which are being detected and come up with a conclusion which says what is the residual useful life, or when the maintenance should be done, or isolate where the problems are actually arising in which part of the machine. So from this is basically the idea of preventive maintenance, and it's a major kind of it's becoming a very major part of industry 4.0 as we call it today. Okay, so predictive maintenance or preventive maintenance is a major aspect of sensor technology and networking today. Okay. So if you have any questions, please go ahead. Otherwise, we'll go to the next video quickly. No questions? Okay, so we'll just quickly go to the second video on accelerometers.
Have you ever wondered how your phone manages to know what direction you're holding it? It's using a device called an accelerometer. It works by sensing the acceleration of gravity, and then you can calculate what direction the phone is facing. But how does a piece of electronics sense something mechanical like acceleration? The answer is MEMS, micro-electromechanical systems. MEMS are kind of like silicon integrated circuits, but they're mechanical in nature. MEMS manufacturers use similar techniques that are used to make electronics, but instead they're making tiny mechanical structures that can interface to electronics, allowing you to build some interesting things. Here I've got some MEMS dies that I made out of silicon. They contain a lot of the same basic structures that you might find in a modern MEMS chip. Let's take a look under the microscope. This is a tiny resistor. The lighter colored material is actually electrically conductive silicon, and this darker area that's been etched away doesn't conduct. This long winding electrical path forms a resistor, very similar to how a long piece of wire would also have a significant resistance. So if you made an electrical connection between these 2 points, you'd have a microscopic resistor. Now, in order to understand how an accelerometer works, let's look at a MEMS capacitor. It doesn't look much like a capacitor, does it? Well, remember that all a capacitor really is 2 conductive plates that are electrically separated. Here are the 2 terminals of the capacitor. Over here, we have what's called a combed finger arrangement. The 2 structures are very close to each other, but they aren't quite touching. Let me highlight it for you. Now it should be more obvious that you have parallel surfaces which form a capacitor. But this is no ordinary capacitor. It's a physical structure that can move. This thing over here is basically a tiny weight made out of silicon, and it's kind of like a suspended mass on the end of a spring. Movement, vibrations, and even gravity can cause this little mass to move around, and when it does, it shifts the entire combed finger structure. When the fingers move, the distance between the fingers changes. And when the distance between the fingers changes, you get a change in capacitance. So now we have an electromechanical system that can sense movement and turn it into a changing capacitance value. The next step would be to design circuitry that can sense the change in capacitance and convert it into useful voltages or serial data, but that's beyond the scope of this tutorial. A modern MEMS accelerometer will contain structures similar to this, except with even more fingers to increase the surface area, which increases the capacitance, which makes changes in acceleration easier to detect. Here's another electromechanical capacitor, except it senses acceleration on the horizontal axis. Ignore this, that'll buff right out. When the suspended mass moves in the horizontal direction, the surface area between the fingers changes, and then you can have some electronics to sense the change in capacitance again. Now, if you want to play around with accelerometers at home, you don't need a microscope. You can go to a company like Adafruit and buy a PCB with an accelerometer chip on it. Just power it with 5 volts between Vin and ground, and you'll get voltages that correspond to acceleration on the X, Y, and Z axes. Now you know how an accelerometer works. Thanks for watching. Have you ever wondered how
Right, so that is the overall idea behind accelerometers in the uh, industry as well as when you're doing practical stuff. So MEMS type, most of the accelerometers that you will find in the what do you say? Most of the devices that you will find being manufactured for your lab applications and all that, they are all MEMS type of sensors, and they will be ideally manufactured by either companies like Analog Devices or by companies like Honeywell Automation. So that is what we expect, and I think we are out of time. Any queries on accelerometers? Hello?
No, sir.
Yes. So I think you people are okay with this. I will share the presentation as it is after the slides are over. So please keep this with you, and you can revise this as and when time passes, and you can keep up you can remind this kind of questions may come for the interview also, because you are supposed to know from end to end how the whole process happens. So right from sensor to signal processing to data visualization, that is UI UX design, you should have a complete understanding of the process. That's what computer and communication engineers are supposed to know. So let's hope this is useful in the future also. So we'll continue with this in the next class. Meanwhile, if you have any queries or any suggestions, please feel free to contact me. You can WhatsApp me, email, or whatever other means of communication you would like to follow. You can contact me regarding this. Or if you want any specific topic to be covered, I can do that as well. So you can send me that suggestion as well. If you're not willing to say that in the common meeting, you can send it to me separately. I'll include it as a part of the lecture itself. Okay. So thank you all for attending. If there are no questions, I think we can break. Just a moment, I'll just download the attendance. Just give me a second. Okay. Thank you all for attending. We'll continue in the next class. Bye.
Thank you, sir.
Thank you, sir.
Thank you, sir.